In this video, we will be going over the basics of IR spectroscopy. Now, please keep in mind that we will go into more depth of this topic in Chem 227, but this will provide you with enough information that will allow you to analyze your products that you make in lab for the rest of the semester. Now, IR spectroscopy is a method used for looking at bonds. And by looking at bonds, it allows it to be a good method for detecting different functional groups. So if we think about the functional groups are made up of a variety of bonds. So for instance, this is an ester, but the ester contains a C double bond O, so that's one type of bond. It also contains an oxygen connected to a carbon, so that's another main type of bond. In the alcohol over here, we also have a variety of bonds. We have an oxygen bound to a hydrogen, that's one type. We have the oxygen bound to the carbon, and then we also have carbon bound to 3 hydrogens. So again, a variety of types of bonds in this alcohol. Now, IR spectroscopy is based on infrared energy. So this is our electromagnetic spectrum, and IR is going to be located over here near the microwave and near infrared area. So bonds interact with IR radiation in specific ways, and that will allow us to know what types of bonds are in different types of molecules. We are lucky to have an IR machine on campus that we will be able to use throughout the year. Now, the basic way that an IR machine works is it contains an IR radiation source, and in the presence of no sample, certain frequencies will be detected or read by the machine. Now, in the presence of a sample, that IR radiation source will go through, pass through the sample, but only certain frequencies will be detected. The difference will tell us which frequencies were absorbed by the molecule or by the sample. Okay, so the machine knows what frequencies it can read, but when there's a sample present, only certain frequencies will be read since the other ones will be absorbed by the bonds in the molecule. When bonds absorb IR radiation, it causes vibrational excitation. Now, there are several types of vibrations that can result when the bonds absorb that radiation or that energy. So the one we will be focusing on are stretching vibrations. And with stretching vibrations, you can imagine that the bond between two atoms is actually more like a spring. So when the energy hits the bond, it's going to cause the two atoms to move back and forth in a springing motion. With an in-plane bending vibration, also known as scissoring, when the bonds absorb the IR radiation, it causes the atoms to move up and down in a similar way as if you took a pair of scissors and opened them and shut them. Okay, so they would come closer together, farther away. With the out-of-plane bending vibration, the best way to visualize this is hold out your two arms up and in a V shape, and then twist side to side from your waist. So that's going to illustrate how the out-of-plane bending vibration would be. Now again, we're going to be focusing on the stretching vibrations. Now, the frequency of each stretching vibration depends on two things, and they're somewhat related to one another. First, the size of the atoms. Small atoms absorb at high frequencies. So when you have bonds between small atoms, they're actually going to be stronger bonds. And that's because the electrons in smaller atoms are held closest to the nucleus of the atom. So bonds between small atoms are stronger and are going to take a lot more energy to cause a vibration. Related to that is bond stiffness, where stiffer bonds absorb at higher frequencies. Again, the stiffer or stronger a bond, the more energy is going to be required to cause it to vibrate. An IR spectrum is organized by wave number. The wave numbers are located here on the bottom of the graph. Now the wave number is calculated from this simple formula of the frequency of light that is absorbed by the bond divided by the speed of light. Now since the speed of light is constant, the wave number is entirely dependent on the frequency of light, of the frequency of the IR radiation that is absorbed by the molecule. So over here, 400 represents a lower frequency, 4000 represents a higher frequency. There are two main regions on an IR spectrum. We have the diagnostic region, and the diagnostic region is the most useful to us because it will let us know what types of bonds, it contains the types of bonds that are found in the most common functional groups. The diagnostic region is located from 1500 and above, and that's what we will be focusing on for all of our IR spectra. The fingerprint region, which is about 1500 and below, is exactly what it sounds like. It's a fingerprint. So the fingerprint region is unique to each molecule, just like your fingerprint is unique to you. This region can get very, very complicated, so we're not going to be really looking at it at all in this class, with the exception of occasionally looking at a C that is bound to an oxygen. Now, just as we saw, there are two main things that depend or that determine what frequency is absorbed by a particular bond. So the size of the atoms, the small atoms, absorb at a higher frequency. H is the smallest atom that we have, so as you can see, all bonds to H are going to absorb at the highest frequencies possible. We also consider bond stiffness. So triple bonds are stiffer or stronger than double bonds. So as we can see, the triple bonds do absorb at a higher frequency at around that 2100 to 2300 range. Double bonds, which are a little bit weaker than triple bonds but still stronger than single bonds, absorb in about the 1600 to 1815 range. Now this is an example of an actual IR spectrum. So on the bottom you can see that we have the wave number, and this is going to vary from 400 to 4000, just as we see above. Now here on the y-axis we have the percent transmittance. Now the IR is actually kind of upside down. These are the peaks and they dip down. Now the further down that a peak goes, the stronger that signal is. So we're actually going to be focusing on the peaks that come down closer to the bottom of the IR spectrum. The little things up here are just noise and can be ignored. We will go through several of the most common peaks and bonds that we'll see in IR data, starting with CH bonds. Now these are the most common types of bonds. Every organic molecule contains a carbon bound to a hydrogen. Now even though all CH bonds are a carbon single bonded to a hydrogen, the strength of that bond will vary depending on what type of orbital the shared electrons are held in. So if the H is bound to an sp3 hybridized carbon like we see here, this is actually going to be the weakest bond and at the lowest frequency. It's going to be around 2900. And that's because an sp3 orbital has 75% p character, which means it's actually more of a dumbbell shape. And that dumbbell shape means that the electrons are held further from the nucleus of the atom, which makes the bond weaker. So in general, all of our hydrogens bound to carbon atoms that are sp3 hybridized will show up just below 3000 at 2900. Now, in general, what I have you guys do is draw a line right at 3000. Anything that's to the right would represent a carbon that is bound to an sp3 hybridized carbon. Now, for sp2 hybridized carbons, again, we have a carbon that's single bound to an H, but this sp2 hybridization means that the orbital is only 67% p character, so it's a little bit less. That means that it's going to have a slightly more spherical shape, a little less dumbbell shape. That spherical shape allows these electrons to be held closer to the nucleus of carbon and strengthens the bond. So that stronger bond means that it's going to absorb the radiation at a higher energy, around 3100. So again, if we draw this line down 3000, anything that's just to the left of it, slightly above, will represent a hydrogen bound to an sp2 hybridized carbon. And lastly, this is a lot less common, but when you have a hydrogen bound to an sp hybridized carbon, These orbitals are 50% S character and 50% P character. So again, that increase in S character, that spherical shape, means that these electrons are held really close to the nucleus of carbon, strengthening the bond, and therefore they're going to absorb at a higher frequency of around 3300. So this is going to be a big difference between our sp2 and sp3 hybridized carbons, but it will be above that 3000 range. Now, carbonyls, or C double bond O's, give very strong absorption peaks at around 1630 to 1780. Now, these are some of the peaks that we are able to see very easily on an IR spectrum. So again, a strong peak is going to be one that comes further down on the IR spectrum. So this peak here is exactly what we would expect a carbonyl to look like. So C double bond O tends to be very strong, coming further down on the graph. Something else that's a double bond, such as a C double bound to a C, is going to be a little weaker signal, so the peak's not going to come as far down. Alcohols also give very strong absorption peaks. Alcohols are slightly different in that they're going to be giving a broad absorption peak, and that's going to be around 3200 to 3550. Again, this higher frequency is because we are bound to the small hydrogen atom. Now, the reason that OH peaks are broad has to do with the fact that OH peaks are capable of participating in hydrogen bonding. We will not be talking about any OH peaks that do not participate in hydrogen bonding until Chem 227. So for our purposes in this class, we are always going to see a broad absorption for representing an OH peak. So we saw in the previous slide that carbonyls and OHs give very strong distinctive peaks. Now if we take a look at carboxylic acids, a carboxylic acid contains a carbonyl as well as an OH peak. So we're actually going to, an OH bond. So we're actually going to see two peaks representing these two different types of bonds. So remember that IR looks at bonds, and by looking at the bonds, it helps us determine functional groups. So for carboxylic acids, we expect to see a C double bond O represented at around 1700. And we see this strong peak at around 1700. So this strong peak here is representing our carbonyl from the carboxylic acid. For the OH, we saw previously that alcohols have very strong broad peaks for the OH bond. For a carboxylic acid, it's actually even broader. So a carboxylic acid OH peak can range from about 2500 to 3600, and it's actually going to take up the whole space like we see here. Okay, so if we see something where a lot of the 2500 to 3500 range is taken up, plus a carbonyl, it indicates that we have a carboxylic acid. Next we have amines, and we're only going to be focusing on primary amines, which are bound to 2 hydrogen atoms, and secondary amines, which are bound to 1. So since the nitrogen is bound to a hydrogen, it's going to show up in that higher frequency range, most commonly associated with the bonds to hydrogen. A tertiary amine is bound to 3 carbons and has no hydrogens, and so we don't really use IR to detect tertiary amines. Now for a primary amine, since we have 2 bonds to 2 H's, we're actually going to see 2 peaks in the 3300 range. Okay, so 2 peaks for 2 NH bonds. For a secondary amine, where we have 1 NH bond, it's going to be 1 peak in that 3300 range. Okay, so it comes up in around the same range as the alcohols, the OH bonds, but with the alcohol we see that broad, strong peak. With the nitrogens, we see a little bit weaker signals and either 2 peaks for a primary amine or 1 peak for a secondary amine. You will often be asked to characterize the IR data that you collect in lab. So in several of the experiments this semester, you're actually going to make a molecule, and then once you make it and purify it, you're going to go and take an IR spectrum using the IR machine in the lab. So once you have that data, I will ask you to analyze it, and that's what I mean by characterizing the data. So there's a few simple steps to follow in order to characterize it properly. So I've shown here a IR spectrum for this molecule here, and this is eugenol from clove oil. We're actually going to be isolating this from cloves a little bit later. But first what we're going to do is on your IR spectrum, you're actually going to draw the molecule. And you can draw it wherever there's space. Some people draw it here, some people draw it up here if there's space. Wherever you can put it, you always want to have the molecule directly drawn on the IR spectrum. Then you want to identify and label as many of the major peaks as possible based on the bonds in the structure. So if we take a look at eugenol, we have an OH bond. We have a benzene ring. We have a bunch of hydrogens that are not drawn in, but they're certainly there. So we've got hydrogens bound to sp2 hybridized carbons, another hydrogen, set of hydrogens bound to sp2 hybridized carbons. We have hydrogens bound to sp3 hybridized carbons, again over here, sp3. So even before we take a look at the data, we can just take a look at the molecule and see what we would expect to find. Now we know that an OH peak is very strong and broad, and it comes out at around 3,200 to 3,600. And what you can do is you can use this chart that's over here, and I'm actually going to provide this for you to download and print out. But you can use this to kind of help you remember where you're going to end up finding those bonds. So in OH, it's around that 3,200 to 3,600 range, and it is broad. We also have carbons that are sp2 hybridized bound to hydrogens. Again, coming over here, taking a look at this chart. Now the highlighted portions represent the bonds that these frequencies represent. So over here, we've got a hydrogen bound to a carbon, and if we take a look at this carbon, it is sp2 hybridized. Same down here, we've got a hydrogen bound to a carbon that's sp2 hybridized in a benzene ring. You'll notice that both of these bonds come out at the same place on the IR chart at just above 3,000. So we would expect to find some peaks greater than 3,000. We also have hydrogens that are sp3 hybridized. And again, if we take a look at the chart, we've got carbon hydrogen, this one's sp, sp2, sp2. Here we've got a carbon that's sp3 hybridized. And again, we can see that those peaks will come out just below 3,000. So that's what we would expect to find. Okay. So now let's just go ahead and we're actually going to label the peaks that we see directly on the IR spectrum. So we know that the OH comes out at around the 3,200 to 3,600 region. We've got a strong bond peak here. So I'm going to go ahead and label this as my OH bond. Next, I'm going to draw a line directly up the 3,000. That's going to be my dividing line. Now, anything that is higher than 3,000 is going to represent my carbons that are sp2 hybridized bound to a hydrogen. So I'll just label that here, that these set of peaks just above 3,000, just to the left, represent the CH bonds where the carbons are sp2 hybridized. Then for our sp3 hybridized carbons, those are going to be to the right, just below our 3,000. And again, we'll label it here. Now we'll take a look. We do have, so we're going to use 1,500 as kind of our mark. Anything to the left of 1,500 we'll want to try and characterize. Now, we also have a benzene ring. If we take a look at our chart, benzene rings provide two bands at around 1500 and 1600. You can see a bond at 15, a bond at about 16. So we'll go ahead and say that these two are representing our benzene ring. And at this point, we are done. We have taken into account all of the bonds that can possibly fall in the diagnostic region, and we have now fully characterized our IR data. So you will most often characterize your data on data that you collect in lab. Now, in your homework or worksheets, you're often going to be doing multiple choice or matching types of problems. So there's a different type of approach you would take in this case. So you would be provided the IR data. You would also be provided or be allowed to use your chart with the common absorption frequencies. So let's say we have this IR data and we're trying to match it to one of these three molecules. Now in this case, what we would do stepwise is we would look at the strongest peaks that are only in the diagnostic region. So we really want to focus on 1500 up to about 4000. From there, we want to identify the major bonds using the absorption table. Then we can match to a molecule containing those combination of bonds. So we are going to focus from here on. There's really two major peaks that we need to characterize. So for the one here, it falls just below that 3000 range. And if we go over to our absorption table, we can see that we've got just below 3000 here represents a carbon that is sp3 hybridized bound to a hydrogen. Then we've got a strong broad peak at around 3400-ish. Now we know that OHs are broad, they are strong, and they also fall in that range. So this can represent an OH. Okay, so now we want to go down to our molecules. Our first molecule contains an OH, and it also contains several hydrogens bound to sp3 hybridized carbons. So this is a good candidate, but let's go ahead and make sure it's not any of the other molecules. Our second molecule also contains an OH. It contains H's bound to sp3 hybridized carbons, but also we've got H's bound to sp2 hybridized carbons. Since we don't see any peaks above that 3000 region, it cannot be this molecule. And lastly, we've got a carboxylic acid. So we have an OH, but we also have a C double bond O. Now a C double bond O is always going to appear in that 1700 range. Now notice in our chart, you are given several different types of carbonyls. These are just showing exact numbers or in general where you would expect these carbonyls to appear. The main thing that I want you to take away from this table is that carbonyls can appear anywhere from about 1650 to about 1800. So you don't have to worry too much about getting these numbers exactly right. We would just know to look on the chart and see if we have a peak in this region, and if so, if it could possibly correspond to a carbonyl. Now we have no peak in this region, so this cannot be the molecule. All right, so this is the only one that can match the data that has been provided. You will have lots of practice with IR in the next few weeks. In Experiment 8, you will use IR to help you identify an unknown compound. For one of your online labs, you'll be completing an IR worksheet. When we isolate essential oil from cloves, we'll be able to analyze the essential oil using IR. We will use IR to make sure that we have made our molecule 4-methylcyclohexene in Experiment 24. And we will also use it to confirm that we have made T-pentyl chloride in Experiment 23. So I would recommend printing out the IR absorption table and bringing it with you to lab so that you are able to analyze your data as you get it.